Quantum technology is a bit of modern research that's focused on taking a part of physics that's quantum physics. It's the physics of really, really small things, single particles of matter like atoms or single particles of light like photons. Taking the parts of that theory that for ages were thought to be just weird math, things that Einstein made fun of. All the great minds of the 20th century actively tried to demonstrate why this math was just so crazy that it had to be wrong. Taking that and building things with it. It's kind of a remarkable thing that even though quantum mechanics has buried inside of it all of these extremely unusual effects, unusual from the perspective of our daily experience, all of them have been shown to be real. They've all been shown to be things we can measure in laboratories. These are concepts that you sometimes hear about, like a particle is really a particle and a wave. That has a very specific meaning in quantum mechanics. It's kind of the best way we can, in a cartoon way, express it. Other ideas like a particle can be in two places at once, or the famous thought experiment that a cat can be dead and alive at the same time. This is called Schrodinger's cat. It was a thought experiment. All of the underlying physics is real. And it's so different than our daily existence, our daily experience. But what's happened over the past, say, decade is that scientists and technologists like myself, my own research group, have gotten very good at controlling individual quantum mechanical systems, single atoms, single particles of light called photons, and using them in order to gain access to these phenomena and then try to make them do useful things. Well, an exciting part of what's going on in quantum science and quantum technology is, as I said, that many of these phenomena that for many years were thought to be nothing more than mathematics are being demonstrated to be real, that quantum mechanics in its fullness is being shown to be the accurate representation of reality, and that our ability to access these things and use them is growing. So in quantum mechanics are some very, very unusual phenomena. In addition to the ones I talked about before, there's the notion of teleportation. Now, when I say this, I don't mean Star Trek style, beam me up, Scotty, but the idea of taking information and sending it instantly over any distance is something that really exists in quantum mechanics. And it's something that you can do in the laboratory. Groups like the one I worked for when I was in Boulder, Colorado, had done this in the early 2000s. It's been around for quite some time. So the idea that in the future, quantum teleportation may actually be a resource to power technology is really exciting. And who knows, in the long term, it may even be that we're teleporting whole things because we maybe have to describe reality by quantum mechanical wave functions. You take all that quantum information and you send it somewhere else. That's at least possible. Maybe not likely, but at least possible. But then there are other things that come from the kind of technology we're trying to build. One area of technology that we're working very hard on is called, very broadly, quantum computing. And there's a niche within that called quantum simulation. So it's a little bit like making a scale model of an airplane and studying how that behaves to understand how to design a full aircraft. You build the scale model, you study it, it's a lot easier, and then you gain insights about how the big airplane is going to behave. Well, we're taking that concept and applying it in the context of quantum mechanical systems, because there are many, many problems in physics and material science and chemistry that are really hard to solve on any conceivable supercomputer because those systems are governed by the rules of quantum physics. It's just very difficult to model. So instead of the brute force approach where I take your laptop and you try and build a numerical model, I'm trying to build a quantum scale model using technologies that harness these weird quantum effects. So you're making a one-to-one match with the system you want to solve within the space of what we think we might be able to do. We think we might be able to use this kind of system in order to solve a particular problem in material science related to why certain materials that are ceramics at room temperature, like dinner plates, why they turn into conductors for electricity. They allow current to flow with no resistance. Now, resistance is what makes your toaster element heat up, but it's also just a source of loss. The energy that's carried by current gets lost when you send it over wires. So these materials are really hard to simulate, they're very hard to understand, and after 30 years or so, one class of them, we still don't understand why they work. We have very little idea. We think we might be able to make a quantum scale model from the ground up using the technology that we build in order to mimic the behavior of these really weird materials. If we do that, we may be able to gain insights into how we make superconductors that work at room temperature. Now, that might sound crazy and sci-fi enough, but there's more. So if you can make these quantum simulators, solve the problem of why superconductors superconduct, and then engineer materials that superconduct at room temperature, now you have the ability to think about building an energy superhighway where you can send energy over any distance with no loss. Now there's a precedent here, which is the fact that the information superhighway, the fiber optic network that now is covering everywhere in the globe, that works and has given us the information economy because of our ability to send data over huge distances with no loss. So now, imagine you build an energy superhighway. You send energy over any distance with no loss, anywhere in the world. What can you do with that? Well, the craziest thing that comes to my mind, because I like thinking about these things, is you can terraform. If you can go to a desert with energy, you can turn that desert into arable farmland because maybe there's an ocean nearby and you do desalination and you can make chemical fertilizers. You have plenty of energy. The great thing about this is it also frees us up to use clean energy. Right now, a major impediment for us using offshore wind or tidal generation is that you can't send that energy over big distances because it gets lost in the wires. So the whole paradigm of how we generate and then distribute energy could change if we do this. And it all starts from research harnessing quantum physics. Well, I think what we'll see at first is a set of small changes in the kind of power of our technologies. I mean, whether you know it or not, almost everything that governs our daily lives works because of our understanding of quantum physics. Microprocessors, the internet, all of this works because of our understanding of quantum physics. The next step is harnessing these weird bits that I talked about and using them to build new things. And as I said, the first set of developments will be reasonably small. One great example of early quantum technology is atomic clocks, and these are what make GPS work. GPS works because we have really precise timekeeping instruments. What's going to happen is that these clocks will get better and better, and GPS will get more and more accurate. That's a reasonably straightforward thing. But then the exciting things come when we think about building quantum simulators for solving problems in materials or chemistry that have eluded us for decades or in some cases even centuries. Things like the Haber-Bosch process. This is a great example. It's a chemical process that is how we make fertilizer. We make ammonia-based fertilizer. And it's extremely inefficient. It consumes about 5% of the Earth's natural gas output annually, just making fertilizer. Because there really isn't an efficient catalyst, a kind of a material that allows the reaction to happen with low energy. And what's exciting is that in our community, some scientists in Switzerland at ETH have posited that with small-scale quantum simulators, quantum computers, you might be able to solve the problem of how you make a catalyst for this process. All of a sudden, you overcome this challenge that for 116 years has cost us to use so much energy in making fertilizer. So now agriculture becomes efficient. That's an enormous change. Challenges associated with feeding the global population with limited resources without spending so much natural gas. Those problems are overcome. And then you can even imagine a completely different paradigm for processing information that renders obsolete all of the public key encryption systems that we use for secure transactions. You can really boggle your own mind thinking about what would happen if all of these technologies come to fruition. And the exciting thing for me is that that's only what we've been smart enough to think of so far, right? The most exciting things are what we haven't even realized. And so that's what motivates me in the morning.